Hola, chaps. Let's learn.
Hola, chaps. Mr. Turek here. This is primarily for chemistry, but it also applies for physics students as you review thermochemistry, right, Pratika? All right. So what I have here is a generic heating curve. The y-axis is temperature. The x-axis is how much energy I add to it as a function of time, typically. And for all, not for all, but for most substances, the curve has this shape. At absolute zero, it's in a solid state. As I add heat energy to it, it becomes a hotter solid. At some point, it can melt. And as I continue to add energy to it, the temperature does not increase until it has melted. Then, adding more energy, it's now in a liquid state, but it doesn't just go and become hotter and hotter as a liquid. There comes a condition for given pressure where it begins to boil and transform from a liquid state into a gas state, and then that increases in temperature. Coming down the curve, I cool a gas, and it doesn't end up as a cold gas. It reaches its freezing, what do I say? Its boiling point, where it condenses as we remove energy from it. Then is transformed into a liquid. The liquid cools down, but at some point it will reach its freezing point where it transforms from a liquid into a solid, and then it can be cooled down theoretically to zero if we could get that far. So I want to practice this equation. It's the first one on the reference sheet that you students now have on our Google Classroom. This is the Physics and Chemistry reference sheet from June 5th, 2019. And the front side, again, has the Greek prefixes you should all have memorized. The back side has the equations that are relevant to this section of the course dealing with thermodynamics. So the first equation up here is Q equals mc delta T. That's the one I want to start off with. So Q is the amount of heat energy, M is the mass, C is the specific heat, delta T is the temperature. I randomly picked one of the substances from this table. There are a dozen substances here. Alphabetical order, melting point, boiling point, the specific heat that it has. So melting point would be here on the graph. Boiling point would be up here on the graph. Specific heat is the slope of this first line. Specific heat for the liquid state is the slope of this line, and it can be quite different from the others. The specific heat in the gas phase is the slope of this line up here, and again, it can be different from these other two slopes. The heat of fusion is how much energy it takes to go this horizontal dash. The heat of vaporization is how much energy it takes to traverse this horizontal dash. So I could add to that and put here delta H of fusion and delta H of vaporization as terms that now you're responsible for, right? All right, I'm going to work an example. If I go too fast, just play the video again. So, randomly selected methanol in a liquid state. Noting that it's a liquid between its melting and boiling points between negative 98 degrees Celsius and positive 65 degrees Celsius, I'm going to just pick an initial temperature of negative 5 degrees for a mass of 234 grams and a final temperature of 42 degrees Celsius. And the challenge is calculate, please, how much energy does it take to heat liquid methanol of this amount, 234 grams, from this temperature to that temperature? Well, the formula is Q equals mc delta T. So mc delta T means 234 grams, because this table of information is in units of grams, no need to convert to kilograms, times the specific heat. If it's starting at -5 and that's above its melting point and it's ending at 42 degrees and that's below its boiling point, then it must be in the liquid state. So I use the specific heat for methanol in the liquid state, and it says the value is 2.597. So 2.597 joules per gram per degree C. And now I need to plug in the change in temperature. All right, well, so if if you've forgotten, the change in temperature is always the final temperature minus the initial temperature. So in this situation, it's 42 minus -5. You love minus signs. Therefore, it's really 42 plus 5, which means 47 degrees C. Now, I mentioned this in a previous video. Let me reiterate. If the temperature is given to you in Kelvin, you can still use these values from this table because a change of 1 degree in Kelvin is equivalent to a change of 1 degree Celsius. Between Celsius and Fahrenheit, it's different, but between Kelvin and Celsius, it's the same. So you're going to get the same result. Now power up your calculator. Beat me to the punchline, please. Calculate how much energy does it take in this situation. And I don't think you can see that because of the glare, but I probably could dim this. And then we can see both of these things without you having too much change in your overall contrast. Yeah, you can see that. You can see this without that, and I can still read it. So I have a Q value of 28.6 kilojoules. Now you're going to say, well, wait a minute. On the calculator, it said 28,561.806. Yeah, well, so, use your Greek prefixes and round to 3 sig figs. So there you go, 28.6 kilojoules. Let's just keep working examples because maybe you need this. All right, now, suppose I have this same amount of energy, the same mass, I want to change one thing. And basically what I want to change is the substance. So I want to keep the energy just to make a new problem. Keep the mass, change the substance, and see what the new change in temperature would be. Okay, so, what substance could it possibly be? This is going to take me a long time if I just keep randomly doing things slowly. And I'm not too fond of doing things randomly slowly all day long, but for once, here we go. It says transform it into acetone. Random number 1, 2, 12, and it came up as a 1. So for acetone, I don't have very complete information. I don't know its melting point because it's probably so cold that it hasn't been measured very well. Its boiling point is 57 degrees Celsius. I don't know what its specific heat is in a solid state. I don't even know the temperature at which it freezes. I don't know the specific heat in a gas state. I don't know the heat of vaporization. Interestingly enough, they have a value for the heat of fusion, even though they don't have a melting point for acetone. So probably Lord Google has some information that can fill in some of these blanks. But for us for today, It clearly must be in the liquid state. And so what's new here is that the specific heat has changed from the value for methanol into the value for acetone, which is 2.184 joules per gram per degree Celsius. All right, so now I'm going to rearrange the original equation. And this time I'm solving for delta T. So not knowing what the melting point is for acetone, but knowing that it's got to be low because I've worked with acetone, I'm going to say, suppose that the initial temperature is again -5 degrees Celsius, but this time, what's the unknown is the final temperature. Everything else is given. The mass is 234 grams. The substance is acetone. Specific heat, liquid state, initial temperature, -5 degrees, and Q is already given. It's 28.6 kilojoules. So I'm going to take all the energy it took from the first problem, problem one, and use that as the starting value for here, problem two, which is what I scribbled over here. All right, so in this case, I need to rearrange the original equation to solve for delta T. Delta T is equal to Q divided by M divided by the specific heat. Okay, so here's where you and I might have a small discrepancy. I have not cleared my calculator. Yes, I have. So I'm going to use 28,600 joules. So if you didn't clear your calculator from the last problem, this is rounded off from 28,561.806. I'm starting off saying it's 28,600 joules. I'm going to divide that by 234 grams. I'm now going to divide this by the specific heat of acetone, 2.184 joules per gram per degree Celsius, and beep, 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 I get a delta T of 56.0 degrees Celsius. So it's 55.96255556. Great. So if my initial temperature was -5 degrees, think of it this way. Once again, change the temperature. Oh, I suppose it should go a little bit more like this. And focus it. Is equal to final temperature minus the initial temperature. So therefore, the final temperature is equal to the initial temperature plus the change in temperature. Algebra. And therefore, in this problem, the final temperature must be -5 degrees C, my starting temperature, plus an increase of 56, we're going to call this point 0 degrees C, and you end up with 51.0 degrees C as the final temperature for acetone. This is for a mass of 234 grams of liquid acetone starting at 5 degrees below 0 Celsius. When I add 28,600 joules of energy to it, what is the final temperature? Why, the answer is 51.0 degrees. All right, so let's keep going. Let's say that my final temperature is 51.6 degrees. And what shall I change now? So I changed what the substance was. First, we were given everything except Q. The next time, we were given everything except delta T. How about this time, I give you everything except the mass, okay? So I'm going to take some random numbers. And what's going to be unknown will be the mass. Q equals mc delta T. And I want to go way faster than just picking numbers using a calculator. So I have silver. And turns out I have 23,400 joules of energy. Okay. And this is probably, oh, wow. It's either solid or liquid silver. Okay. I'll say it's solid silver. And the initial temperature is, let's use that last problem, 51 degrees. The final temperature is about 42 degrees. So I'm cooling it down this time. I'm removing, so I guess I should say Q is minus 23,400 joules, correction. The heat that I remove is going to be 23,400 joules from solid silver. It was at an initial temperature of 42 degrees. Sorry, initial temperature 51 degrees, final temperature 42 degrees. Calculate, please, how much mass of silver is involved in this made up problem. Okay, well, so Q equals mc delta T. M is therefore equal to Q divided by C delta T. In this case, it's going to be 23,400 joules. I guess I could put negative if I want. And I'm going to use the specific heat of solid silver, which is 0.235. So 0.235 joules per gram per degree C. And the change in temperature, 42 degrees minus 51 degrees, is negative 9.0 degrees C. And since Q is also negative, a negative divided by negative, they're going to cancel out. That's why I'm too lazy to write it in the first place. So you can't have a negative mass, and so you should be able to figure that out. All right, calculate, please. I think you can see the result better than me. This is 11.1 kilograms. That is a huge chunk of silver. 11.1 kilograms is well above 22 pounds of this stuff. So it's a silver bar. All right, so much for that example. Next, I want to solve for some unknown substance. And here's where I can be totally off the chart, literally. So on this chart, the specific heats for some solids are listed, and they're from something as low as 0.1 to something as high as 2.2-ish. In the liquid state, it's from about 0.1 again, but it can go as high as 4.7. And in the gas state, there's not a lot known, but between 1.3 and 2.1 or so. So I'm going to make up some random number, and it might be something totally off the chart. And in that case, we'll just have to say, well, what's for that one? So what I want is a mystery substance where we're going to identify it based on its specific heat. All right, so here's some random numbers. Let's say that I have 13,100 joules of energy, that the mass is known to be 230 grams, that the initial temperature is minus 15 degrees C, and the final temperature is 38 degrees C. So what would be the specific heat for this mystery substance? Well, solving for the specific heat, that would be Q divided by M divided by delta T. In this case, 13,100 joules divided by 200, let's make it 3 sig figs, 230 grams. And the change in temperature, so I'm starting at 15 degrees below zero, and I'm ending at 38 degrees above zero. Final minus initial means 38 minus negative 15 is really 53 degrees of change in temperature, right? So into your calculator, 13,100 divided by 230 divided by 53, and the calculator says, aha, this is 1.07 joules per gram per degree C. So what is this mystery substance? I'm going to just look around and see what is the closest number I can find to 1.07 in any of these three columns. And then put in a little caveat. So the closest thing to 1.07 it would be 1.18. Okay, so aluminum, which has a melting point of 660 degrees Celsius, is clearly in the solid state. So best guess solid aluminum. Okay, so because I coincidentally came so close to it, the next challenge question is, so what would be the percent error? That's something that was covered in chemistry course and says, oh, percent error is equal to the difference between what's accepted and what you measure times 100%. So let's treat this table as being accepted value of 1.18. And therefore, if you go 1.18 minus 1.07, divide that by 1.18, multiply that by 100%, then it says, whoa, pretty good for me. Less than 10% difference, okay? So 9.3% error. How's that for just randomly making up numbers? Yeah. Okay. So that's these are 4 examples dealing with this first equation, Q equals MC delta T. practice these equations over and over again. In fact, here's what I'm going to do. I'm going to randomly make up 3 more problems and then pause the tape and then display the solutions. So let's create 3 more problems right now, 3 or 4 more problems. So let's do a problem with solving for Q. So I'm going to say, suppose I have solid, so let's call this practice 1, right? I have solid lead and, what can I say? It's at a mass of 82.7 grams, and the initial temperature is, I want it to be hot enough to melt lead, 110 degrees Celsius. The final temperature is 309 degrees Celsius. Calculate, please, how much heat energy does it take to heat 82.7 grams of solid lead from an initial temperature of 110 degrees Celsius to a final temperature of 309 degrees Celsius. All right, so this practice problem number 1. Practice problem number 2. This time, let's solve for the kind of the same order here. The change in temperature. Okay, so this time I have a heat energy in the amount of 4,210 joules. I have a mass of 159 grams. The substance is gasoline, so clearly that's going to be liquid. Probably shouldn't have picked this though, right? Whoa, who knows what's going to happen here. And we're solving for final temperature. So let's say that the initial temperature is just above its melting point, so it's negative 55 degrees Celsius. The specific heat, if you haven't looked it up on your table already, is 2.220 joules per gram per degree C. And calculate, please, what is the final temperature for this practice problem. Number 3, let's solve for mass this time. Is that right? Yeah, sure, mass. So I have a heat energy of, let's see, May 18th. So 5 for the month and 18 and just add a 0 joules, 5180 joules. I have a substance of copper, and let's make it liquid copper. Okay. And forgot what I'm solving for. Mass, right? Okay. I have an initial temperature, and since this is a liquid state, it's going to have to be above 1,000 degrees. So let's call it 1,220 degrees Celsius. And it has a final temperature of 1,290 degrees Celsius. So how much mass is involved with that liquid copper? And as a fourth problem, practice problem, Hmm. On this one, I could try to have you identify the substance. I got extremely lucky this last time in that I happened to hit something that was somewhere on this chart. And I don't think I can do that without kind of working forward from a particular problem and trying to use values that give you at least a chance of landing somewhere on this table. So maybe for the fourth one, it's going to be some mystery substance that's not even on the table. Okay, substance X. I see that it was at an initial temperature of 2020 degrees Celsius. Good for you seniors. It was at a final temperature of oh 1792 degrees Celsius. This was dealing with a mass of uh, 42.1 grams. And the amount of heat energy, see, this is where it's just like totally random. So let's say the heat energy for this was 876 joules. Calculate, please, what is the specific heat of this mystery substance. And if it happens to be anything close to any of the values on the table, then make an attempt to identify what this mystery substance could possibly be. Keeping in mind that, if the specific heat is close to, let's say, water, but the initial temperature is at 2000 degrees, let me clarify. If this comes close to liquid water, but the temperature was in the thousands of degrees Celsius, it can't really be liquid water. So it's really just substance X. All right, pause your tape and work out the solutions. I'll pause it, work out my solutions, and list them, and that'll end this segment. Okay, I paused. Hopefully you did too, worked out the solutions. For practice problem number one, I got a result of 2,140 joules. Number two, I made this 55.0 degrees Celsius, so I'd have 3 sig figs, and got negative 43.1 degrees Celsius. For number three, I got 151 grams. And for number four, this substance, I forgot to put a minus sign here since my final temperature is below my initial temperature. I must have been removing energy. And therefore, my specific heat for this substance is 0.0913 joules per gram per degree C. I remind you, these leading zeros are placeholders. They're not significant digits. So here's my calculated result to 3 sig figs, not 4, not 5, 3 sig figs. This concludes this video. Now go practice what I've preached.